Hey guys. So in our lab yesterday, we looked at multiple collisions, right? We went from station to station, and we saw that with some collisions, objects stick together. With other ones, they bounce apart, and there's motion afterwards. Before we get back to those collisions, we're going to look at something called momentum. Now, we use momentum in our everyday language. A lot of us already know what it is. If you think of momentum, you might think of a car crash, a football player getting hit, things like that. However, it's very important that in this class we have a scientific definition and, more importantly, an equation to explain momentum. So before we get with that, let's talk about this problem that I posed to you a few days ago. I told you that one of the things they did to help fix Verrucht and make it so the raft was not launching off the slide is that they made the raft smaller. They made it what was a 4-person raft into a 3-person raft. But we talked about that it doesn't matter what the mass is, objects accelerate the same. So even with the fewer amount of people, the raft should still be going the same speed. My question to you was, why did that make a difference? Why did cutting the number of people on the raft down affect that slide? And the answer that a lot of you gave me, and it was perfectly correct, was if you take a person out, it will have less momentum. That's perfect. But what is momentum? Okay, I think we'd all agree that here, if you have a tennis ball, here, if you have the same tennis ball, it's going faster. I think we all would say that the one that's going faster is going to have the larger amount of momentum. So this is telling us that momentum must be directly proportional to the speed of the object or its velocity, v. Down below, it's hard to see, but this is a golf ball and this is a bowling ball. So in this illustration, the golf ball and the bowling ball have the same speed. They have the same velocity. However, they're obviously different in size, right? So if you're asked which has the larger momentum, the golf ball or the bowling ball, going the same speed, you should pick the bowling ball, right? I'd much rather be hit by a golf ball than a bowling ball if they're going the same speed. So this is telling us that momentum must also be directly proportional to the mass of the object, m. So now we're looking at momentum in terms of how fast something is going and how much of that something there is. The velocity and mass both contribute to momentum. So for a very simple definition of what momentum is in this class, we're going to call it mass in motion. Really easy, but I like it easy. Okay, so equation for momentum. We know it has to do with velocity. We know it has to do with mass. Guys, it doesn't get much more simple than this. First of all, we're going to label momentum P. So P stands for the symbol for momentum. Now, a lot of people ask me, why do we use P? Well, M is already taken, correct? M stands for mass. Normally, when someone asks me where the symbol comes from, I tell them it's Latin, and it's usually right, but in this case it really is. The Latin base for momentum started with a P, so that's why we're using P in this equation. Okay, so the equation for momentum is lowercase p is equal to mass times velocity. Multiply the mass of the object times its velocity, and that will be its momentum. Okay, so given that we know this equation now, we have to think about what is momentum measured in. What are the units for momentum? Well, we already know mass is measured in kilograms, correct? We already know that velocity is measured in meters per second. Therefore, if we have momentum is equal to mass times velocity, I'll rewrite that down here, and we're talking about the units, then that will equal a kilogram multiplied by a meter per second. Therefore, the units for momentum can be written as a kilogram meter per second. Okay, now something I want you to remember is that a newton is really measured as a kilogram meter per second squared. That's really close to what we just have down here, except for the second is not squared on the bottom. So another way we can write the units for momentum is as a newton second. Okay, so your units for momentum, you can either write them as a kilogram meter per second, or you can write it as a newton second. Either one will be correct, and I'll accept both. I tend to prefer to write it as a newton second. It's just less to write than a kilogram meter per second. Alright, now let's try some problems. These examples are not too hard, but let's give them a shot together so we know what we're doing. Example 1, a ball of mass 0.5 kilograms starts to roll on the ground with a speed of 5 meters per second. Calculate the momentum of the ball when it starts rolling. Well, we just learned that momentum is equal to mass times velocity. Well, this is pretty simple. They gave us a mass of 0.5 kilograms, so 0.5 times our velocity, which was 5 meters per second. 0.5 times 5, in other words, half of 5, will give you an answer of 2.5. And you can plug that in the calculator if you're not the best at math. Okay, now we need a unit. We just talked about there's two ways to write the unit. So you can write this as a newton second, or you can write it as 2.5 kilogram meters per second. Either answer is correct. Okay, now it's telling us that after 10 seconds, the speed of the ball changed. So after 10 seconds, it only had a speed of 2 meters per second. It slowed down a bit. It's asking you to calculate the momentum now after it has slowed down. Momentum is still mass times velocity. So our momentum will equal, it's the same mass because it's the same object. So 0.5 for our mass. We're multiplying this by our new velocity of 2. Half of 2, I think everyone knows, is 1. So 1, make sure you label it, newton second is your answer for part B. Okay, so sometimes we study just one object, and we spend a lot of time just studying one object. However, last unit, not this unit that we just finished, but the unit before that, we learned about analyzing multiple objects. And when you study more than one object, you call the multiple objects a system. Should sound somewhat familiar. Okay, so when you're talking about the total momentum of an entire system, what you have to do is sum or add the momentum of each separate object. What that would look like in an equation, it's pretty simple, is momentum total, so I'm going to write total down below it here, is equal to the momentum of each individual object. So the momentum of object number 1 plus the momentum of object number 2 plus, if you have it, momentum of object number 3, and that just continues for how many objects are in your system. So to do an example using that equation, example 2 says Paul is playing with two identical rocks. Each has a mass of 0.2 kilograms. He throws the first rock up with initial speed of 5 meters per second. He throws the second rock down with an initial speed of also 5 meters per second. On part A, we have to calculate the momentum of each rock, specify the direction. So once again, momentum, just mass times velocity. So let's do the momentum of rock 1. The momentum of rock 1 is equal to the mass of the rock, which they told us, 0.2 kilograms, multiplied by the velocity of the rock, which for the first rock was 5. Okay, I did a positive 5 on this because the first rock was thrown upward. So 0.2 times 5 once again gives us that momentum of 2.5 Newton seconds. That was for rock 1. Now if you look at it, the only difference about rock 2 was the same mass, but it had a speed of 5 meters per second in the downward direction. What that is going to change is that this velocity will now be negative. So for rock 2, we have the same mass of 0.2, but we're multiplying it times 5 this time. I just realized this. This is not 0.5 times 5, this is 0.2 times 5. I made a mistake. 0.2 times 5 gives you an answer of 1, not 2.5. I apologize there, guys. Okay, back to rock 2. This is now a negative 5, not a positive. So your answer is the same, but it's in the negative direction. So the momentum of rock 1 is 1 Newton second. The momentum of rock 2 is negative 1 Newton seconds. On part B, it says calculate the total momentum of the system. The system is made up of both the rocks. So to make a momentum of the system, it's pretty easy. We add the two together. So the momentum total is equal to the momentum of rock 1 plus the momentum of rock 2. So I'm going to write P with a little t down below, is equal to the momentum of rock 1, which was 1 Newton second, plus the momentum of rock 2, which was negative 1. So when we have 1 and we're subtracting 1 from it, we end up with a momentum of 0. 0 Newton seconds. So because one was completely opposite the other, their momentums essentially cancel out. So the momentum total for the system ended up being 0.